Hey, hi everybody. This is the second. Hi everybody. This is the second lecture in the Ramanujan Explained series. I have now put up some notes and some exercises, so I hope some students can benefit from that. I just want to say that this is dinner time in China, so there is Shishwa Fu has put some, and his students have are placing these lectures in a site which is accessible in China too. So let me begin. Okay, so this lecture is on the q-binomial theorem. That's it's the smallest of all the binomial theorems, the q theorems which Ramanujan had, and this is in chapter 16. So this is what the theorem says, and I will explain what each of these terms mean, and we will prove it. And in fact, the proof is also due to Ramanujan. So it's one of those proofs which have come in one of his papers, and I will present his proof over there, which I suppose could also be said to be joint work with Hardy, because Hardy used to, uh, you know, help Ramanujan with his papers. So last time um, we saw. So last time there was this notation of q rising factorials. Yeah, not so clear. Right, that will pick up. So there were terms such as these, AQ. So this is what we defined q rising factorials as. So for k bigger than 0, it was 1 minus a, 1 minus aq, and so on till 1 minus aq to the k minus 1. And so there are k terms here. And so we usually just use the product notation and write it like this: 1 minus aq to the j. So this is called a q rising factorial, and we also use this notation when k is equal to infinity. 1 minus aq to the j. So you can regard this as a formal power series or as an analytic function. And we haven't really done how to define infinite products, etc. But we will do at some point. So this is in Q, and Q is called the base. Q is called the base. So these series are often series associated with such products are referred as basic hypergeometric series. The base comes from this Q, and there are certain facts which we will prove at some point. So when if we look at ZQ infinity, so we look at ZQ infinity as a function of Q. Then this product, so for fixed Z, some complex number, this product converges, the product converges for absolute value of q less than 1. So again, q could be a complex number, and it converges for any z. And this we will prove, and it converges absolutely, in fact. And we could also so for a fixed q with absolute value of q less than 1, we can also regard it as a function of z, and it is entire, which means it's analytic for all z. So both these facts we will prove at some point. So proof is deferred when we do infinite products, but we might as well get used to these products, to manipulating these products first. So some remarks on these products. If you take aq infinity and you divide by aq to the kq infinity, then if you can cancel various terms and get 1 minus aq to the j, and that's aq sub k. So the q rising factorial with finite products, you can look at it as ratio of two products. And if k is not an integer, we can use this. So if k is not an integer, a positive integer, we can use this idea to define q rising factorials. So if it's not a non-negative integer, so what is it? I mean, it could be any complex number, and we can use this idea to define it. If we take the limit as q goes to 1 of just aqk, then this is the limit as q goes to 1 of the product of 1 minus aq to the j. So this is just 1 minus a raised to the power k. So here j is going between 0 and k minus 1. So it's just this. So this limit should be aq infinity over aq to the k q infinity. This is also equal to 1 minus a to the k. So this expression makes sense for both sides, even when k is not a non-negative integer. So in fact, here is an entry due to Ramanujan. So Ramanujan's first entry, 6. So in volume 3 of Byrne, chapter 16, the first entry, it has several parts. The first part is exactly this. Limit as q goes to 1 of qq infinity over aq to the x q infinity is equal to 1 minus a to the x. So this makes sense when absolute value of a is less than 1. This side, and you know, a cannot be 1. So this thing cannot be 0 inside. So there's a complex number you can define. So let me put it as 3. For a less than 1, the right-hand side here can be expanded using the binomial theorem. And so this somehow this is this will be used in subsequently many times. And there is one more limit which is very important, which, so if you just take q raised per a sub qk, so q rising factorial, and divide it by 1 minus q raised per k and take the limit. So this is a limit from calculus. So you on the top you have 1 minus q raised per a, 1 minus q raised per a plus 1, and so on. 1 minus q to the a plus k minus 1. And at the bottom you have 1 minus q, 1 minus q, and so on. And each of these, you can take the limit. So this is this chap right here. This is denoted as a sub k. This is a rising factorial. And so this is the definition. So I should say, you can define the rising factorial like this. And we note that 1 sub k is k factorial. So this justifies these terms. You know, rising factorial and also q rising factorials. All right, so so this is just some notations. Let me show you. There was a function which I mentioned in the exercises. Let me just examine that for a bit. So this is EQZ, which was defined to be this summation from k going from 0 to infinity. So just an example of a kind of result that we have. This is QQK, and this is equal to 1 over CQ infinity. So this is a result of Euler, and this part, this equality, the discovery of how to discover this is an exercise in chapter 1. So you, by using Euler's trick. So what we'll show is, so we show that this sum converges for absolute value of z less than 1, provided absolute value of q is less than 1. So how do we do that? I mean, let's do ratio test. So let tk be equal to z raised per k over qk. Then tk plus 1 over tk, the absolute value of that. So that's z raised per k plus 1 over z. And at the bottom, you have 1 minus q, 1 minus q to the k, 1 minus q to the k plus 1. So this comes from q k plus 1, and on the top you have 1 minus q, and so on up till 1 minus q to the k. And the whole thing, so right here is an absolute value. So this gets cancelled and you get z, and most of these cancel, and you get 1 over 1 minus q to the k plus 1. And this goes to absolute value of z when k goes to infinity, because this guy is going to 0, right? This q raised power k plus 1 goes to 0. So by the ratio test, the series tk converges when absolute value of z is less than 1. So this is about as tough a convergence test required in almost all of Q series. So it's quite an important thing to understand how to do this. This is as tough as it would get in most of Q series, as far as convergence of series goes, and products will also be very similar, which we will come to at some point. Now, in this result, suppose if we put replace z by 1 z times 1 minus q, so and then take the limit. So we get eq of z 1 minus q, which is the series z raised per k 1 minus q raised per k over q k going from 0 to infinity, and we take limit as q goes to 1. So you notice just that, let's just look at this term wise, k, this is equal to the limit as q goes to 1, z raised per k, 1 minus q to the k, and here you get 1 minus q, 1 minus q squared, and so on. So you get k factorial using the same limit. Again, this is as difficult as it gets taking limits here. This limit we are using. Oops. So this is just saying that this function q raised to the power a has derivative of a at q equal to 1. Right. So so if we do that, so what we get is term-wise EQZ tends to this series z raised per k over k factorial. So which is the exponential function. So this is term-wise, and you can justify that the limit is actually this because this converges uniformly and absolutely. So in any subset, compact subsets of Z, it will converge uniform to this. So there's no problem in convergence here. And we say EQ Z is a Q analog of E raised per Z. And I say a Q analog because there are more useful Q analogs. Right. So so this is actually this result is actually a special case of the Q binomial, which is our objective today. We will prove it. Q binomial. It's to be placed somewhere. All right. So to summarize so far, um, we just did the notation for the Q rising factorials, and here is one special case of the Q binomial theorem, which you can discover for yourself using the same technique as we used last time to discover the product side of the Rogers-Ramanujan identities, and we will prove it shortly uh, when we do the Q binomial theorem. So, but before that, I want to uh, show you another idea, is how to guess or discover the binomial theorem. Um, I would say Newton's binomial theorem. And again, this kind of thinking is quite useful for us. So you know, pay attention. Okay, so what are we doing? We know, so the finite form, this is easy to prove. This is proved in using induction or in elementary courses, and we will also get some proof today. But at present, let's just take it for granted. So n choose k x to the k. So here n choose k, this guy, this is n choose k, and this is equal to n factorial over k factorial over n minus k factorial. It's the number of ways of choosing k objects, k subsets of an n set. Right, and this we want to generalize it. So what did Newton do? So Newton. So this is okay for n equal to 0, 1, 2, 3. This was known for centuries before Newton. What Newton did was Newton replaced n by a. N is not a non-negative integer. Right. So what Newton did was he did that. So how do we guess a general result? That's the point. So let me put here. So let me write it again. So it's 1 plus x raised power n, which is equal to k going from 0 to n. Sorry about that. I somehow got thrown out. Now I don't know exactly where I was. So maybe Surbi, can you tell me?
Yeah, so you were going to get to the general result.
Okay, so this part was covered.
Yeah, it was covered.
Okay, and we were looking at Newton's binomial theorem.
Right, right. And then you were going to generalize it, like why we needed the general result.
Okay, okay. All right. Sorry about that. Some disaster with the internet. So this is the result. This is the binomial theorem, and we want to generalize it or guess what would the answer be if n is not a non-negative integer. So if n is a, so the left-hand side, there is no problem. So left-hand side makes sense. So the left-hand side makes sense if n is replaced by a, and a could be a, you can take it to be a real number or even a complex number. So if it's a complex number, then we have to sort of define it like exponential of log of 1 plus x times a. So 1 plus x to the a would be defined like this, and then you have to take care that the log is complex log. But it works, it can be done, and anyway, for real numbers, just think of it as a real number, this is fine. Now, the right-hand side, there are two places where n comes. So there is this place over here. So this has to be replaced somehow by a. So what we could do is we could just write it as k going from 0 to infinity. And then there is no such thing. So you observe that n choose k is 0. So n choose k is 0 for k bigger than n. So might as well just write it like this. And now, so it's an infinite series. Now, you still want an n here, so we can write it like this, n minus 1, n minus k plus 1 over k factorial. And now we can replace, you can replace n by a. So this gets transformed into k going from 0 to infinity, a minus 1, a minus k plus 1 over k factorial. So this should be equal to 1 minus x raised per a, 1 plus x raised per a. So this makes sense. The series converges for absolute value of x less than 1. And it makes sense. And in fact, that is Newton's result. So what I will do is I will outline a proof in the, so we will outline a proof using calculus in the exercises. And, you know, usually we would write it like this. So we would write it as minus a plus 1 and so on up till minus a plus k minus 1 divided by k factorial, and there's a minus x to the k. So usually one would write it like this: minus a sub k over k factorial over minus x raised per k. So, I mean, you can remember it best in this form, but you can write it in terms of rising factorials. So, so what we want is a Q analog of this. Okay, so I will outline a proof, and I think I'm not even sure if Newton proved it, but it can be proved using Taylor series. So using the machinery that Newton made. So I'll outline a proof of this so that this is also covered. I mean, this is one of the fundamental theorems in this whole area. So it's a good idea to be quite familiar with it. Okay, so now finally we get to a q-binomial theorem. And I want to give Ramanujan's proof here. And this is entry, so volume 3, 16, and the second entry. And it says that so this is the theorem. Let absolute value of q less than 1 and a less than 1, then minus b q infinity over a q infinity. This is how it's stated in Bruce Burns' book and by Ramanujan. I mean, Ramanujan didn't use the q rising factorial notation, but he had it like this: a raised per k. All right, so proof, and this is due to Ramanujan. So in my notes, I'll give a reference. It's actually within one of his published papers. He needed this result, so he proved it. Consider this function abz equal to bzq infinity over azq infinity. So this is k going from 0 to infinity, 1 minus bz q to the k over 1 minus azq. So we had seen such products came up in the Rogers-Ramanujan identity, so it's quite natural to consider some kind of thing like this, and we expand it as a power series. So you could take it to be a formal power series. So z square and so on in Z. So expand as a formal power series in Z. So there's no Z here, it's just additional, but you just expand it over here. And then what you can see very easily is that if you multiply the left-hand side with 1 minus AZ, F A B Z, and take out the first term and the second term, so what you will get is 1 minus BZ. So if you do that, then it will start with, it will have F with Z replaced by ZQ. So 1 minus AZ, and this is a power series, 1 plus A1Z plus so on is equal to 1 minus BZ. This will be A0 plus A1ZQ plus A2Z square Q square plus 1. And now if you compare coefficients of Z raised per Q on both sides, or Z raised per K or N, what am I using? K. On both sides, then so for K bigger than 0, then on this side you will get from the first guy you will get AK, from the second guy you will get A times AK minus 1. And then on the right hand side, you'll get Q raised per K from Z raised per K, Q raised per K, AK minus B, AK minus 1, Q raised per K minus 1. Right, so this will mean that AK 1 minus Q raised per K will be equal to A minus BQ K minus 1, AK minus 1. So which is the same thing as 1 minus BQ K minus 1 over A AK minus 1. So then you can iterate it. So 1 minus BQ to the K minus 1 over A, 1 minus BQ to the K minus 2 over A square, AK minus 2, and so on, till you get to the last step, which will be 1 minus BQ to the K minus 1 over A. Keep reducing powers till you reach 1 over B by A, and there will be K of them, and you have A0. And sorry, there is a denominator here. So, okay, I should say so. Hang on. This here. So AK is 1 minus BQ to the K minus 1 over A divided by 1 minus Q raised per K A times AK minus 1. So now we can iterate this and oops. Oops. Let's rewrite it. So if I iterate it, I'll get BQ to the K minus 1 over A square. One more time. So on until we reach this guy divided by 1 minus Q to the K. So this will be divided by 1 minus Q raised per K, 1 minus Q to the K minus 1, going on to 1 minus Q. Right. So, well, what is A0? A0 is 1. Why is that? So if you just go back to the same thing, if you put Z equal to 0, you'll get A0, which is going to be 1. So this is A0 is 1. So ultimately you get as formal power series. So we get FABZ, which was BZQ infinity over AZQ infinity. That's equal to the summation K going from 0 to infinity. So the AKth term is this guy, which is B by A sub K, Q sub K, and QQ sub K. And there's a raised per K and a Z raised per K. And now Z is redundant. This parameter Z is redundant. It's not needed really. So we can get rid of it. So we take A going to A over Z, B going to minus B over Z to get it in the form that Ramanujan wanted. So for some reason, Ramanujan had a minus B here, K going from 0 to infinity of minus B by A Q K over Q Q K A raised by K. And so this is a formal derivation, and you can so again we have to get used to the formal derivations, but this proof works even as analytic identity. So the remark is the proof works as an analytic identity, and we require where we need A less than 1 for the series to converge and Q less than 1 for both series and both products and series. So we had seen the convergence of this kind of series. It's just with one term, and it works. So usually the q-binomial theorem is written as azq infinity over zq infinity, which is equal to summation k going from 0 to infinity, aqk over qqk, z raised per k. So this is for absolute value of z less than 1, absolute value of q less. Ramanujan wrote it slightly differently. He liked to keep these products like this, and it's useful for us later to keep this form because we want to see what Ramanujan did. So both sides, both these sides, they work out, and we should say provided the denominators are never 0. On either side. And I want to state another fact, which we will prove at some point, that CQ infinity is 0 only when Z is Q raised per 0, Q raised per 1, Q square, and so on. So ZQ infinity is what? It's 1 minus Z, 1 minus ZQ, and so on. So whenever these terms are, any of these terms are 0, then it's 0, of course, but we'll prove that it's actually only at these points. So it requires some proof. So we'll prove this later again as part of our thing. So that finishes it. Let me do one small example before I stop. Suppose we take, suppose A is equal to Q raised per minus N for some N bigger than equal to 0. So we notice that Q raised per minus N Z Q infinity over ZQ infinity this is equal to, so this is what the theorem boils down to, Q raised per minus N Q K over Q Q K, Z raised per K. Now this chap right here, we notice that this guy, Q raised per minus N Q K, is 1 minus Q raised per minus N, 1 minus Q raised per minus N plus 1, so on. So at some point, minus N plus K minus 1. So when K becomes bigger than N, so this becomes 0 when K is bigger than N. So the sum becomes finite. Terminating sum. And we get summation Q raised per minus N Q K over Q Q K, Z raised per K. And this guy on the left-hand side, so on the left-hand side, you will get 1 minus, you will get Q raised per minus, so you'll get 1 minus Q raised per minus N Z, 1 minus Q raised per minus N plus 1 Z, and so on. At some point, you'll get minus Z, and the rest of the terms will cancel. So rest of the terms will cancel with, so this is Q raised per minus 1, maybe. And then you will get ZQ infinite, 1 minus Z, and so on. So all the terms will cancel. So if we replace Z by ZQ to the N on both sides, then we will get 1 minus Z 1 minus zq, and so on up till 1 minus zq to the n minus 1. And here you get, so this will be k to the n, k going from 0 to n, q raised to minus n qk, q and z to the k, q raised per n k. And this is a short exercise that you can k going from 0 to n. You can write this as qqn, qqk, and qqn minus k, and minus 1 raised per k, z raised per k. So this is an exercise. Now, in this, if we take q going to 1, if you take q goes to 1, then you will get 1 minus z raised per n is equal to k going from 0 to n, and choose k minus z. This is the binomial finite form. So yeah, I will stop here. If there are any questions, we can take some questions now. Okay, any questions? Okay, then let me stop the recording.